Have you ever wondered where black holes come from? These cosmic phenomena, as enigmatic as they are powerful, have a fascinating origin story. It all begins with a star, not just any star, but a massive one. When these stellar giants have used up their nuclear fuel, they're left with a heavy heart. This heart, or core if you prefer, is so dense, so heavy, that it cannot withstand its own gravity, so it collapses. This is what we call a gravitational collapse. But not every star gets to become a black hole. There's a tipping point, a critical limit, beyond which a star's core must weigh to transform into a black hole. This limit is known as the Chandrasekhar limit, named after the Indian astrophysicist Subramanian Chandrasekhar. Imagine it like a cosmic scale. If the core's mass is lighter than the Chandrasekhar limit, it shrinks into a dense, hot white dwarf. But if it's heavier, then the core's fate is sealed. It continues to collapse, shrinking smaller and smaller, denser and denser, until it becomes a point of infinite density. This point is what we call a singularity, and it's shrouded by a region from which nothing can escape, the event horizon. And voila, a black hole is born. But the story doesn't end there. Oh no, the birth of a black hole is only the beginning. As it grows, it feeds on the surrounding matter, sucking in gas, dust, and even other stars. Its gravitational pull is so strong that not even light can escape its grasp. So, black holes are born from the death of massive stars. Quite a celestial paradox, isn't it? Imagine a boundary that once crossed, there's no coming back. That's the event horizon. This invisible line in the cosmos is the defining feature of a black hole. Anything that crosses this boundary is drawn inexorably towards the black hole's center, a place of infinite density known as the singularity. Picture yourself standing on the edge of a vast abyss. The event horizon is that edge, and the abyss is the singularity. The singularity is where our understanding of physics and reality breaks down. It's a place where the very fabric of space-time becomes infinitely warped, and all matter is crushed to an infinitesimal point. So what happens when something crosses the event horizon? Well, it's a bit like being pulled into a cosmic drain. Once something crosses that boundary, it's forever lost to the black hole's singularity, disappearing from our observable universe. It's the ultimate point of no return, a boundary that even light cannot cross. Not all black holes are created equal. Surprised? Well, let's dive into the cosmic variety show of black holes. First up, we have the stellar black holes. These are the most common type, and they're born from the dramatic death of massive stars. When a star exhausts its nuclear fuel, it goes out with a bang in a supernova explosion, leaving behind a core that collapses under its own gravity. If this core's mass is a few to tens times the mass of our sun, it becomes a stellar black hole. Next, we have the supermassive black holes, the real heavyweights of the universe. These giants lurk at the centers of galaxies, including our own Milky Way. They boast millions to billions of solar masses. But how do they form? That's still a cosmic mystery. Some theories suggest they might grow from stellar black holes, gobbling up matter and merging with other black holes. Finally, we have the Goldilocks of black holes, the intermediate black holes. These elusive entities have masses that fall between stellar and supermassive black holes. They could be the missing link that helps us understand the growth process from stellar to supermassive black holes. However, their existence is still a topic of debate among astronomers. From stellar to supermassive, black holes come in different sizes, each with its unique cosmic tale. Black holes are invisible, yet their presence is felt in the cosmos. Just as a puppeteer pulls strings to control marionettes, black holes manipulate the universe, unseen but undeniably influential. Emitting no light, they are essentially invisible. So how do we even know they exist? The answer lies in their gravitational effects on nearby matter. Picture this, a colossal cosmic entity shrouded in mystery, exerting such a powerful gravitational pull that it warps the very fabric of space-time around it. This warping causes nearby objects like stars and gas clouds to move in distinctive ways, often spiraling in orbits around the black hole. By observing these movements, astronomers can infer the presence of a black hole even if they can't see it directly. Think of it as cosmic detective work. Just as detectives piece together clues to solve a mystery, astronomers study the behavior of celestial objects to detect the presence of black holes. It's akin to figuring out there's a whirlpool in a river, not by seeing the whirlpool itself, but by noticing how the water around it swirls and churns. The effects of a black hole's gravity can even reach light itself. Yes, that's right, the fastest thing in the universe, traveling at a staggering speed of around 300,000 kilometers per second, bends under the gravitational influence of a black hole. This phenomenon, known as gravitational lensing, can produce extraordinary visual effects like arcs, rings, and multiple images of distant galaxies and quasars. So, while black holes remain enshrouded in darkness, they leave an indelible mark on their surroundings. Their immense gravitational pull dictates the movements of nearby celestial objects and even bends the path of light itself. In this way, black holes, though unseen, reveal their presence and influence in the cosmos. Invisible yet influential, black holes truly are the silent puppeteers of the cosmos. Did you know black holes aren't completely dark? Yes, you heard it right. The enigma that is a black hole doesn't stop at its event horizon. There's a fascinating phenomenon that takes place right at this threshold, called Hawking radiation. Quantum physics, the science that describes the strange happenings in the world of the very small, predicts this faint radiation. So how does this work? Well, let's dive into it. Near the event horizon of a black hole, pairs of virtual particles and antiparticles spontaneously pop into existence. This is a common occurrence throughout the universe, but near a black hole it takes a unique turn. Typically, these pairs annihilate each other almost as quickly as they form, but near the event horizon, one particle might fall into the black hole while the other escapes. When this happens, the escaping particle becomes real and contributes to what we call Hawking radiation. However, before you start imagining a glowing black hole, let me temper your expectations. This radiation is incredibly faint, especially for stellar black holes. It's so weak that it's nearly impossible to observe directly. But its mere existence, the idea that black holes can emit anything at all, is a thrilling testament to the beautifully complex nature of our universe. Hawking radiation, a faint whisper in the cosmic silence, reminds us of the enigmatic nature of black holes. It's yet another piece in the cosmic jigsaw puzzle that continues to baffle and fascinate us. The first known black hole, Cygnus X1, was identified in 1971, but how do we study these invisible entities? Unseen, unfathomable, and yet undeniably riveting, black holes have long captured the curiosity of scientists. But the question remains, how do we study something we can't even see? The answer, as it turns out, lies in the ingenious use of technology and the laws of physics. Firstly, we have telescopes. Now you might be thinking, wait a minute, didn't you just say black holes are invisible? And you're absolutely correct. However, telescopes don't just observe light. They can also detect other forms of electromagnetic radiation. X-ray telescopes, for instance, can spot the high-energy radiation emitted by matter just before it plunges into a black hole. Then there are gravitational wave detectors. Gravitational waves are ripples in the fabric of spacetime, created by violent cosmic events like the collision of black holes. By observing these waves, scientists can gather invaluable information about the black holes involved in these cataclysmic events. But studying black holes isn't just about detection. It's also about interpretation, and that's where computer models come into play. Scientists use these models to simulate the behavior of black holes, predicting how they interact with their surroundings and with each other. These simulations can provide critical insights into the nature of these cosmic enigmas. And let's not forget the power of collaboration. International teams of scientists work together, sharing data and insights to piece together the puzzle that is the black hole. Through their collective efforts, our understanding of these celestial mysteries continues to grow, one discovery at a time. From their discovery to ongoing exploration, black holes continue to fascinate and challenge our understanding of the universe. As we delve deeper into the cosmos, who knows what other secrets we may uncover about these intriguing, invisible entities? So, what are black holes really? Birthed from the gravitational collapse of massive stars, these cosmic conundrums have an event horizon from which nothing escapes. They come in various sizes, from stellar to supermassive, and remain unseen until they interact with nearby matter. They even emit Hawking radiation, a faint elusive phenomenon, and our understanding of them has grown since the discovery of Cygnus X1. Black holes, regions where gravity's grip is so fierce that even light bends to its will, are as enigmatic as they are fascinating. They remind us of the endless mysteries the cosmos holds.